Hello everyone and welcome to Memory Forensics for Incident Response. I'm Jason Keeler with the SANS Institute and I will be moderating this webcast. Today's featured speaker is Hal Pomeranz with Deer Run and the SANS Institute. Before I turn things over to Hal, the Q&A portion will take place at the end of the webcast, but please feel free to submit your questions at any point by using the chat window. Right now I'd like to introduce our featured speaker, Hal Pomeranz.
Hey everybody, I hope your Monday isn't treating you too badly. I honestly expected fewer people to be here, it being a Monday and all, but I'm delighted to see everyone. Let's see here. So I wanted to kind of explain a little bit where this talk came from. Last month I was asked to give a presentation for a group, that they're primarily interested in audit, maybe IT management. They weren't as, sort of hardcore tech weenies as the typical SANS audience. And I wanted to say something interesting to them about memory forensics, because I sort of like the challenge of trying to present a sort of deeply technical subject to a bunch of people who don't sort of grovel around in the internals as much as I do. And what I came up with was this notion of creating a presentation that was about, what is the kind of 20% that gets you 80% of the way there? What are a few simple heuristic things that you can do with memory analysis and memory forensics to detect, at least malware infection, so that you can, alert the incident response team at your organization or whoever, deals with that for you that, yes, we have a problem. Yes, the system is infected and we need to take action. Because modern malware is difficult for a lot of organizations to even detect. We're kind of falling down on just sort of basic, is it infected? Because modern malware has frankly become quite adept at hiding itself from kind of typical endpoint protection schemes that most enterprises are using. So that's really the goal of this talk, is something that you could take back and give to sort of the frontline people, your systems admins, your IT operations people, and say, hey, if you think there may be a problem with the system, check these 3 or 4 things really quick, and here's how to do it. And you don't even really need to understand the sort of deep technical stuff, although we'll talk about that a little bit as we go along as well. Throw your questions into the chat window at any time, and I'll try and respond to them as I move along through the presentation. So, why memory forensics? Because everything goes through the memory. Everything happens in memory. You may have malware that comes in as a packed and obfuscated executable, but in order to execute, it needs to be fully unpacked in the memory. All of the actions that malware does on the system, making network connections, modifying data in the registry, all of that stuff, that also is reflected in the memory. And if you know how to look at the memory in a systematic fashion, you can actually very rapidly detect sort of classic patterns that malware uses over and over again to infect your system. There's also lots of other stuff in memory that we talk about in more detail in other SANS classes. Chat, email, encryption keys, all of this other stuff, which we're not going to go into this presentation. But there's just a huge treasure trove of information once you start learning how to unlock the memory of a system. So, modern malware these days, it's very good at hiding, as I mentioned, from sort of traditional endpoint protection kinds of things. It can have a very minimal impact or footprint on the disk of the system. In fact, we're starting to see malware that is purely memory resident, or at most there's a small loader that lives on your hard drive as a sort of persistence mechanism, but the actual functioning malware is downloaded from somewhere else into the memory of the computer. And so sometimes analyzing the memory is the only way to see what's going on with the malware. Also, particularly, nasty packers and things like that can be hard to get through when you're doing static analysis. You may be able to dump the unpacked executable directly out of memory and analyze it there. So there's a whole bunch of stuff that the malware, when it's sort of in its dormant form or just sort of living on the dead disk drive of the system, is hard to detect. But when you look at the memory of the system, it lights up like a Christmas tree. You're sort of taking a outside, almost hypervisor-like position to analyze the system, and as a result, it's much more difficult for the malware to hide from you. And certain behaviors of the malware make it pop up when you start looking at it with these memory analysis tools. So, memory forensics then is just like sort of traditional dead drive computer forensics. It's imaging, that is being able to capture a memory image from one of several different locations. We'll talk about that a little bit, and then being able to analyze that image in a sensible way. Now, back in the olden dark ages of memory forensics, I mean, you were kind of hunting around and doing string searching, and it was gross because you didn't have any context of where these things that you were finding in memory, what process memory the string hit was part of, or any of that. The good news is that, particularly in the last, I would say, 3 to 5 years, we've started to see some really, really amazingly useful memory analysis tools coming out. And I've got to talk about a couple of different ones, Mandiant's Redline and the open source Volatility project, which are just amazing. I mean, they pack a whole bunch of useful analysis that's sort of done for you. So it's almost like having somebody sort of standing over your shoulder and saying, look at this, look at this, look at this. I mean, you don't need to have, sort of this deep knowledge of, Windows internals to figure out what's going on. And so you use these tools to look for stuff that's interesting, for some value of interesting. And I'm just going to quickly point out, some of the stuff that you should be interested in as far as looking for malware and signs of, a malware infection on a system. All right, so step one is getting the memory dump somehow, right? And there are, many tools out there, some free, some commercial, for dumping the memory from a live system. In this conversation, I'm just going to talk about Windows. There are similar tools for, Linux and Mac, but I'm just going to focus in on Windows malware for right now. So there's a bunch of different tools out there, some of which are listed on this slide. Dumpit is a easy to use tool from Moonsols. Moonsols is actually the company that was put together by Matthew Sweesh, who also wrote Win32 and Win64DD, which you also see listed here. But Dumpit basically takes the functionality of Win32 and Win64DD and puts it into a sort of nice wrapper. So you basically install Dumpit on a thumb drive, and then you plug the thumb drive into the system whose memory image you want to dump, and it dumps the memory image to the thumb drive so that you don't end up, potentially forensically corrupting the disk of the system by dumping the memory image there. So Dumpit is cool. I mean, obviously you need to have a thumb drive that's large enough to handle the memory dump of the system. So if it's a server and it's got 32 gig of RAM in it, you need a 64 gig thumb drive to hold the memory image plus the Dumpit program. But that aside, I mean, Dumpit is a quick and easy way to take a memory image from a live system. Win32 and Win64DD are nice as little command line tools. You can run them over PSExec remotely. They are capable of dumping the memory image over the network to another machine, so that's useful. The Redline tool that we'll be using for analysis is also capable of taking memory images. You can also install Redline as a portable agent on a thumb drive, just like dump it, so it can dump the memory and analyze the system from the thumb drive. There are a whole bunch of other tools out there. HB Gary has a free tool. F-Response, which is one of the tools we teach in Forensics 508, is a nice enterprise tool. It's a commercial tool. The enterprise forensic tools like Encase Enterprise and things like that now have the ability to dump memory. So there are lots and lots of different ways for dumping memory from a live system. In general, you're looking for something that dumps memory into what we call a raw dump format. It's basically just a byte-for-byte copy of the memory. To the extent that people are using virtualization, I mean, if it's one of your virtual machines that's possibly gotten infected, getting a memory dump from a virtual machine is usually really straightforward. Best if you can at least temporarily suspend the virtual machine. But once you do that, there's usually a file in the directory where the virtual machine is kept that is a memory image of the system. So you just suspend the virtual machine and copy that file. It's the .vmem file under VMware, and so on. The one exception actually is VirtualBox, which unfortunately the .sav file that VirtualBox uses for storing memory is only a partial memory dump. It's actually only the active memory pages in the virtual machine at the moment you suspend it. And unfortunately, that means that the VirtualBox.save files are not useful for the kind of memory analysis tools that we're going to be using. So for VirtualBox virtual machines, you'll need to actually sort of treat them like a live system and use a tool like dump it or Win32, Win64DD to dump the memory of the system. But for all the other virtualization environments, again, suspend the machine, grab a copy of the memory file, and away you go. And that's, how we do a lot of testing is, we set up test virtual machines and infect them with various pieces of malware and then, capture the memory image that way. And it's just a lot easier. The other thing I wanted to mention real quick before we actually get into the analysis is, in a lot of cases, I deal with law enforcement a lot, and so very often I'm dealing with just a dead disk drive, and I don't get a memory dump along with it. And that means too bad, really. But unfortunately, a lot of law enforcement agencies they don't do live forensics. So one thing I'll say is that if it's an image of something like a laptop where there's a hibernation file, that hibernation file is a compressed memory image from the system at the time it was last hibernated. And there are tools you can use to convert that hibernation file into a raw memory dump that you can then use, something like Redline or Volatility on. Volatility, in fact, has a module that will convert hibernation files. Now, I will say that my experience with the Volatility module has been sort of hit and miss. Sometimes it works and sometimes it doesn't. But you can always try it, and if it works, great. If it doesn't work, there's a commercial tool from Moonsolves called Hibernation, which converts hibernation files, and that one always works in my experience. And it's not, it's a commercial tool, but frankly, it's not that expensive, and the Moonsolves people deserve your money. So Hibernation works well for unpacking hibernation files. I mean, this can be really useful. A colleague of mine was working on an investigation where they found a TrueCrypt container in the disk image that they were looking at. They didn't have the TrueCrypt passphrase or keys to unlock the volume, but they were able to unpack the hibernation file, get the TrueCrypt keys out of that memory, and actually unpack the volume that way. So, like I said, this kind of memory forensics is useful for a lot of stuff besides, malware analysis. So, getting into encrypted volumes is another useful thing that you can do with memory analysis and with hibernation files like this. So, just wanted to mention that before we roll along. I had a question. Can malware prevent a tool like Dump It from getting the true contents of the memory. Sort of like, can the malware hide itself from a tool like Dumpit? We certainly haven't seen malware that does that yet. It's hard for me to imagine how the malware would do that. I mean, if I suspend a virtual machine in the middle of a session and then grab the .vmem file, it's difficult for me to imagine how the malware would completely hide itself. Now, we'll be talking about some kernel level rootkits that do some hiding, process hiding and things like that, and potentially the malware could crap up the in-memory data structures used by the system to make it more difficult to find. But the malware has to be careful about that because it doesn't want to render the system inoperable either. Got another question about what tool should you use for which version of Windows and which service pack version. Generally speaking, all of the tools that I've mentioned work across all sort of modern Windows variants. There can sometimes be a brief delay after a new Windows release comes out where the tools need to catch up. But in general, the tools track, and work on all Windows versions from, at least, XP forward. As you can tell by the names, Win32 DD is for dumping 32-bit systems. Win64 DD is for dumping 64-bit systems. But generally they work across all Windows variants. All right, so let's talk a little bit about some malware techniques and ways in which you can detect them with memory forensics. And we're going to start with DLL injection, which is a super common mechanism for malware to infect the system. And I just wanted to sort of quickly explain what DLL injection is. Again, it's not absolutely critical that you understand what's going on here, because I'm just going to show you a couple of heuristics that you can use to detect DLL injection, even if you don't understand the mechanism. DLL injection is always a sign that something is bad on your system. So it's one of these red flags that you can quickly look at on a system. All right, so before we talk about DLL injection, let's talk about what happens normally, right? So you've got a process, which is the blue box here, right? And it's happily running along, doing whatever that process does. Maybe it's a web browser or something like that. And it needs to interact with the operating system. It needs to interact with the operating system kernel, which is the orange box at the bottom of the slide. So generally, there's a whole API, a Windows API that processes use to interact with the operating system. They might call an API call that, I don't know, let's just say it reads some values from the registry, right? That library call that the process calls interacts with a DLL, a system level DLL, in order to talk with the kernel. So the library call invokes a routine out of the DLL, which in turn communicates with the kernel, says, hey, give me this value out of the registry. And the kernel returns that value, which is then presented in some nice way back to your application. And so that's the way things normally work. You want to talk to the operating system. You go through some routine in a DLL which talks to the OS kernel to get the information that you need. So when we talk about DLL injection, what you've got is malicious software has infected the system and achieved some level of privilege on the system. Once it does that, it proceeds to infect other normal applications that are running on the system. And so DLL injection literally means that sort of unsuspecting applications that are run by the user are infected with new code through the malicious software. The malicious software literally pushes a whole new evil DLL, if you will. That's the red rootkit box on the left-hand side of the picture. It literally the malware literally pushes that evil DLL into legitimate user processes. And it does that through sort of a non-standard loading mechanism. And because of that, that injected code is actually very easy to detect when you start doing memory analysis. Now, it's not enough, though, for the malware just to push the malicious code into the unsuspecting process. It also needs to patch, or what we call hook, the legitimate routine in the system DLL so that anytime the user process calls, NTDLL in this case, the routine in NTDLL, it is in fact diverted into the malicious code that was injected by the attacker, right? And that patching or that hooking is also detectable when you start doing memory analysis. And when you see that happening, particularly when you see that happening on a large number of processes on the system, something has gone seriously wrong, right? And so the way you detect DLL injection is, one, detect the injected code because it's not loaded in the normal loading mechanism, and two, detect the patches or the hooks that are made to multiple routines and multiple system DLLs. And the combination of those two things, or any one of those two things, allows you to easily sort of at least know that something bad has happened to your system. Analysis beyond that point requires additional, deep knowledge, but it's very easy to detect that something has gone wrong on the system just by looking for these things. So let's talk about how we detect the bad stuff. So we're going to use a couple of different tools. We're going to use Redline, which is a Windows GUI-based tool that was created by Mandiant. And let me just disclose before we go any further that I do a lot of subcontracting for Mandiant, so I'm not just pimping the mothership. I actually think that Redline's a really useful tool and a great way to get started with memory analysis, but I do have a relationship with Mandiant that I feel like I need to tell people. So we're going to use Redline to take a look at injected code. Redline has a whole bunch of other additional functionality that we won't have time to get into, but I can at least give you a quick Redline demo. And then we'll be using Volatility, which is a command line based tool for analyzing memory. And the different tools do different things better. So it kind of depends upon which you're more comfortable with, GUI versus command line, and also what you're looking for. So the first malware we're going to look at is Zeus. I've been doing a bunch of investigations related to Zeus malware and ACH fraud in my professional life, so I'm sort of, Zeus is an old friend for me. And I have a memory image of a system that was infected with Zeus, actually a virtual machine, so that I can actually show you this is an older Zeus variant, but it'll give you an idea of how this kind of malware works. Now, Zeus is predominantly used for banking and ACH fraud. It is a Trojan that wants to steal banking credentials. It also is capable of doing what we call web injection to intercept logons for standard banking sites. It's a keystroke logger. It has lots and lots of different functionality. But we'll just be looking at how you detect Zeus once it infects the system. So let's take a look at Redline real quick. And I'm actually just going to go ahead and bring up the Redline demo. So here we go. We're going to share this application. How this is going to work with 400 participants, we'll just see. So let's see. Let's bring up Redline. Okay, so if things are good, you all should be able to see the Redline window. Can I get an affirmation, like raise your hand or say something in the chat window? Everybody seeing this? Yeah, okay, good. We're getting some pinging. Okie dokie. So, welcome to Redline. Redline is a sort of multi-pane GUI. If you look up in the upper left-hand corner, you'll see investigative steps. And that is basically guided analysis. The folks who developed Redline are trying to guide you through the process of analyzing a memory image. And we're not going to go through all these different sections, but you can really sort of walk through those steps, and it will lead you by the hand for analyzing the system. Down the left-hand side, you see a list of all of the processes. You see a little circle next to each process. Redline has a scoring system, and basically tries to heuristically detect badness. If it flagged any processes as bad, they would show up as red in that left-hand window. And generally, when Redline flags something as bad and shows it red, you definitely have a problem. What's interesting about this Zeus infected system is that none of the individual processes have reached Redline's scoring threshold for a bad process. So let's, though, take a look at one of the investigative steps, which is I'm going to go with the review memory sections DLL. So I'm going to skip the first couple and jump right into reviewing memory sections. And you'll notice if you look over on the right-hand side, you can see different views. And I've chosen to view the injected memory sections. Okay, so I've clicked on review memory sections DLLs, and then I selected injected memory sections on the right-hand side. If you see anything in this window, right? I mean, if you take those two steps, review memory sections and view injected memory sections, and you see anything listed in this window as being injected, your system is infected, right? I mean, if you talk about sort of simple heuristics that you don't have to understand what's going on, just find the evil. If you see this, you have a problem, right? Because normally you shouldn't see injected code in this way. Now, I wanted to make the screen small enough that it would fit on most people's screens. So there's a bit more to the right. If you scroll the bottom scroller in the middle, you can actually see that pretty much every process on the system has a bit of injected code in it. And this is very typical of a Zeus infection. It injects into essentially every process on the system. And it uses that to keystroke log, capture credentials, and stuff like that. So, like I said, if you see anything on the screen, you're in bad shape. What's also interesting, if I scroll it back to the left, you'll notice that there's the second column is the name column, and there's nothing in the name column for these injected code segments. That's also not a good sign, because it's another indicator that the code was not loaded in the normal fashion. If the injected code was loaded in the normal fashion, you would see in the name column a path name to a DLL, right? And I can show you that if we click over and we look at one of these processes, like, I don't know, Explorer, and we look at the sections in Explorer, you can see in the name column here, most of the code DLLs and things like that have hard drive path names associated with them, all except for the injected one, which is not so much, right? So, yeah, the fact that you don't see a, backed by disk DLL here for this segment of code is another sign that you've got a significant problem. So, these are the kinds of things heuristically that you can look for, just real quick to get a sense of whether something bad has happened on your system. there's a whole bunch of other stuff that you can do with Redline, and we'll talk about hooking. I actually prefer to use Volatility to look for hooks, but you can use Redline to look for hooks as well. With Redline, it's kind of more art than science, though. So I'll show you hooking with Volatility in just a little bit. All right, so let's go back to the slides here a little bit. So that was, just a quick Redline introduction. And let me catch up on the slides. So these are just some slides I put in for later, which kind of go over the stuff I showed you in the live demo. We had a couple of questions as well. We had a question about, can you use Redline to perform live memory analysis, or does it only work on static dumps? Redline absolutely can be used to do live memory analysis. In fact, it actually sort of works better if you're on the live system, because it can do things like check DLL signing and things like that to look for evil on the system. So again, creating a Redline portable agent, and you can read the Redline documentation, which basically means installing Redline on a USB thumb drive so that you can use it for live analysis, is actually a really useful thing. There's another question about how does it, sort of detect that the DLL is injected. I'm actually going to have some more to say about that as we move along. So I'll come back and answer that question again if people are confused. And there's another question about, should you use memory analysis just for infected systems, or should you also use it as part of behavioral analysis when you're investigating malware? I think it's appropriate in both. And when you're doing malware analysis, using memory forensics is a great way to speed up your static malware analysis. I mean, for one thing, if nothing else, you can get the unpacked malicious executable out of the memory of the system, and then you don't have to fight your way through the unpacker in order to be able to start looking at the code. And I should mention that one of the things you can do, having identified an injected memory segment in Redline, like I was showing you in the demo, you can right-click on the injected memory segment, and Redline will dump that memory segment out into a file for you that you can then load into whatever, IDA or whatever you want to do for static analysis, and start looking at the code that way. All right, so let's talk a little bit about Volatility. So Volatility is open source utility. It's created by Volatility Project. There's a whole bunch of really smart people who are working on Volatility. Aaron Walters, Andrew Case, Jamie Levy, Brendan Dolan-Gavitt. These are all people whose names that you probably recognize. And the cool thing about Volatility is, Volatility is really an API more than anything for dealing with memory. Basically, it's an API that lets you easily write Python modules for investigating memory. And so that makes it possible for people to rapidly extend the functionality of Volatility just by popping out new modules. And if you've been paying attention for the last month, in the run-up to Volatility 2.2, the Volatility Project has been doing their month of Volatility plugins, and there have just been some awesome new plugins that have come out in the last 30 days, which are really, really cool. And the latest version of Volatility, it's not just for Windows anymore. There's Linux support, including support for Android mobile phones, which is pretty neat. And they just announced Mac support in the last few months. So that is super, super useful. So we've got this great tool now that's community supported, that is cross-platform. And because it's written in Python, it's also cross-platform in the sense that you can run it anywhere, right? As long as you've got a Python interpreter and the appropriate modules, away you go. I mean, I personally use it on a Unix machine, but that's just me. I'm the Unix guy, right? But you can run it on Windows or wherever you want. So, yay, Volatility. And I'm just going to run through a quick Volatility demo on the same Zeus memory image that I was using for Redline. So let's go ahead and share my PuTTY window here so I can actually get onto a Unix machine and make myself feel better. Okay. All right, so here we are. And if you can't see this window, raise your hand. No, just kidding. So let's just do a quick run through on Volatility. If you're confused and you don't know what to do about Volatility, you can always get help by doing vol.py -- help. I'm going to pipe this into less so that we can take a look at it. So Volatility -- help gives you sort of the basic command line syntax, but if you scroll further down, it actually gives you a list of all the different modules that you can use, and there are literally dozens of modules. And this is actually the old 2.1 version of Volatility. This isn't even the latest and greatest release candidate, which has even more modules in it. But for example, API hooks, which is one of the modules I'll be showing you, is a good way for detecting those hooks in the normal DLLs that I talked about. But there's a whole bunch of stuff in here that's useful. You can dump out basically the same information you'd see in netstat, network connections. You can dump out registry information, which is really cool. You can dump out process listings and a whole bunch of other really useful stuff that unfortunately we don't have time to get into. The basic syntax for Volatility is straightforward. So I mentioned that these injected code segments are loaded in an abnormal fashion. And because they're loaded in an abnormal fashion, you can detect the injected segments because they don't show up in certain data structures or certain lists that the operating system maintains when a module is loaded normally. When a module is loaded normally, the existence of that module is populated into several different data structures in the kernel memory. There's a Volatility module called loader modules that lets you look at those data structures and detect the injected code because the injected code is loaded but it's not listed in one of those lists. So let's talk about how you would run a Volatility module like loader modules. So it's always vol.py, right? And then the name of the module you want to run, and we're going to do loader modules. Right? And then you need to give it the name of the memory image that you want to run it against. And I've got my Zeus.vmem file. This is a Zeus memory image, all right? And again, the output of this can be rather long, so let me pipe this into less so that we can actually sort of see it a screen at a time. All right, so Volatility loader modules goes off and it interrogates those data structures that I was talking about. And you can see sort of towards the middle right side of the output, inload, initmem, and inmem columns. These are the different data structures that Volatility is looking at to see whether the loaded module appears in those lists, all right? And basically, those should always be all true, okay? If you see a loaded module that has a false in any one of those columns, that is generally a sign that that module has been injected, okay? And you can actually see the base memory address where the injected code resides and all of that stuff. So heuristically, what you want to do is run loader modules and look for the falses, right? And if you see any falses, that's probably injected code, and that's certainly a bad thing. So it's Unix, right? So we can do that easily with a little bit of command line kung fu. So I'm going to run loader modules, and I'm going to grep for the falses. Okay, so show me any lines in the loader modules output that contain the word false, right? So away we go. And on a normal system, this should return no output, right? You should get no lines of output. But again, you can see, just like we saw in Redline, you see in almost every process on this system, there's injected code, right? So, again, if you're looking for a heuristic for, looking at whether your system has bad things happening on it or not, volatility, loader modules, pipe to grep false. If you get any output, bad things have happened. Right? So I mentioned that volatility also has, it's the way I prefer to look for the hooks that we also talked about earlier, right? So hooking is when the malware patches the legitimate DLL calls so that it calls the evil injected code rather than the normal DLL call. And volatility has a module called API hooks, which is really good at detecting those hooks. So I'm going to do, instead of loader modules, I'm going to do API hooks. So the neat thing about volatility is once you understand the basic command line syntax, it doesn't take much effort to run the different modules. It's always, volatility, module you want to run, image name, and away you go. So let's take a look at the API hooks output. So, the difficulty with any sort of memory analysis is that you've got to grovel through the memory image and, find the appropriate data structures and decode them. And so that's why there's always this pregnant pause when I invoke a volatility module, because it's doing all of that parsing. So here we've got the API hooks output, and it's showing you basically unexpected patches in standard system DLLs. And there's a lot of output here, including some disassembly of the first 20 bytes or so of the hooked function, which can be useful if you know assembly language. But let's say you know nothing about Windows internals. What are we looking for here that's significant? You see hooking module unknown. Okay, that's a bad sign. Hooking module basically should show you the module where the jump instruction, the hook, is redirecting you. Okay, you can see the hook addressed right above it, but the fact that volatility is not able to tell you what DLL that hook jumps into is not a good sign. Okay, again, it means that the module that it's jumping into was not loaded in the normal fashion, so it can't actually tell you what DLL you're targeting. That is never a good sign. So if you run API hooks and you see hooking module unknown, call for help, right? You've got a significant problem going on. Now, sort of looking deeper at the output, you can actually see the name of the function that was hooked in this case. And this is where you start needing a little bit of programming knowledge and a little Windows internals knowledge. As you scroll down through the API hooks output, you can actually see the different functions that are being hooked. And if you understand what each one of these functions does, it can give you some indication of the functionality of the malware that's on your system, right? So we see NTDLL, NTQuery directory file, okay? So that's basically getting a directory listing. So the fact that the Zeus malware is hooking that function would indicate to me that it has some ability to hide files from the system's administrator, right? So, if it's hooking things that deal with interrogating the registry, then it's capable of hiding registry entries and things like that. So in any event, if you know more about Windows internals, you can actually, from API hooks, get an idea of the functionality of the malware. Okay, so loader modules look for the falses. API hooks look for hooking module unknown, right? So those are your sort of simple base heuristics. And then the last volatility module that I want to show you in this case is the malfind module. So malfind is a little bit different from the other modules in that it looks for the injected code, but it also is capable of and will dump out the injected segments for you automatically so that you can then analyze them. And so because it's dumping out the injected code, you need to give it a directory that you wanted to dump the code into. So I'm just going to tell it to dump into my temp directory. So that's what the extra -d flag is. So, and I'm going to let malfind go, and I'm going to talk about what it's doing while it's going. So basically, malfind looks for injected code by walking what's called the virtual address descriptor tree, or VAD tree, okay? And basically, injected code shows up in the VAD tree with a particular marker that is unique to injected code. So malfind basically just walks through the VAD tree, which is a list of the virtual memory pages in the system, looking for this particular marker that's indicative of injected code. And when it finds it, it dumps the memory segment out for you automatically into the temp directory. And now my temp directory is full of these dump files. You see the .dmp files. So those are the dumped memory regions, and you can then suck those into IDA-Pro. You'll probably need to rebase them a little bit, which is why the memory offsets appear in the file name. And then analyze the code in the injected segment. So the combination of loader modules, API hooks, and malfind are very good for quickly zeroing in on injected code, either by examining the sort of normal internal data structures that are used by the loader, which is what loader modules does, or by walking the VAD tree, which is what malfind does. You can quickly home in on this injected code, which is difficult to find other ways, right? So let's go back to Illuminate here, and I'll see if I can catch up on some questions as well for people. Can Redline read VMEMs? Yes, it absolutely can. A VMEM is really nothing more than a raw memory dump, just like you create with dumpit or Win32DD or anything else. So there's nothing magical about a .vmem file. They're just normal raw memory dumps. Does volatility work directly from dumpit? Yeah, it should just be a raw memory dump. Okay, so there are a couple other questions, but I'll take those at the end if we have a little bit of time. So we've got some summary slides that just summarize the different volatility modules I went through. I wanted to talk, before we run out of time here, about another rootkit technique, which is process hiding. Process hiding is used by what we call DCOM, or direct kernel object manipulation is what that stands for. DCOM style rootkits. A DCOM style rootkit basically gets loaded, gets system privileges, and then because it's achieved elevated privilege, can actually manipulate internal kernel data structures. One of the most common data structures for these decomp style rootkits to manipulate is the linked list of eProcess structures that make up the process list in memory. So every process on the system is represented by one of these eProcess structures that live in memory. And the eProcess structures are linked to one another. They're actually linked in this sort of bidirectional daisy chain. All right, so every process points to its neighboring processes in a big ring. And so when something like task list wants to list all the processes on the system, it just starts with one of the processes and walks around the daisy chain listing each eProcess structure. Right? Now, when a decomp style rootkit wants to hide one or more processes, what it literally does is it removes the process it wants to hide from that daisy chain. So in this case, the decomp style rootkit is hiding winlogon.exe. So it marches around the circle until it finds winlogon.exe, the process it wants to hide, and then changes the pointers, what we call the forward and backward pointers, or flink and blink. So it changes those pointers to basically remove winlogon.exe from the daisy chain. Okay, so now when processes like task list or whatever enumerate the processes on the system, they won't see winlogon.exe because it's not in the linked list anymore. Now you're probably thinking, well, how the hell does the process run? And I mean, it's not in the list of running. If it's not in the list of processes, how is that process ever scheduled in order to actually function? Well, it turns out that process scheduling on Windows is not done in terms of processes. It's done in terms of threads. So each process that you see in this picture will have multiple threads running inside it, and those threads are scheduled and managed by a completely different set of data structures in the kernel. So even though the process has been removed from this linked list, the threads within that process are still scheduled and still execute and still run as normal. You just can't see the process, right? So, the attacker starts up a packet sniffer or a remote command shell or something like that and hides it using this mechanism from the systems administrator. This is a very common decomp style rootkit technique. But again, doing a little memory analysis, you can easily detect these hidden processes. And you think about it, how would you do that, right? I mean, obviously we can get a list of the processes by walking around the linked list, right? But that won't detect the ones that have been hidden by the rootkit. Well, because we have the memory image, we can grovel through the memory image looking for eProcess structures. eProcess structures have a very sort of particular structure, and you can detect them in memory even when they're not part of this linked list. So what do you do then? Well, so what I do is I get the list of processes the normal way by following the linked list, and then I walk over the entire memory image looking for eProcess structures, and I compare the two lists, right? And if there's a process that shows up when I exhaustively interrogate memory that's not in the list of linked processes, then you have a hidden process and you've got a problem. Now, back in the olden days, you had to run two separate volatility modules for this. In fact, there's a whole command line kung fu episode that I wrote about how to do that. But in the newer versions of volatility, there's actually a module that does exactly that detection mechanism. So, and I can just quickly show you that module. It's called PSXView. And what I've got another memory image here from the FU rootkit, which is a popular Windows rootkit. So I'm going to do vol.py PSXView on my FU rootkit image. Now, we'll take a look at the output real quick. It takes a little while for this module to run because first it has to enumerate the processes the normal way, and then it has to scan through the entire memory image looking for eProcess structures. But just like loader modules, right, if you see any columns with a false, generally speaking, you've got a hidden process, right? So, for example, oh look, we've got a hidden, command shell on the system. We've got this WMIPRVSE process, also, hidden process. So when you see, something that shows up as true in the PSScan column, but when you, look at the thread proc or, other columns, and it shows up as false there, you got a hidden process, right? So, PS list, this column here, PS list, is the normal walk around the daisy chain, right? PS scan is the one that enumerates memory. So when you see things that are found by PS scan and not showing up in PS list, it's not a good sign, right? So again, it's a quick way to detect DCOM style process hiding. You don't even need to know what's going on. Just run PSXView and look for the falses. When you have a discrepancy between PS list and PS scan, it's always a problem. There's never a case where this should happen in normal behavior. So when you see the discrepancy between those two columns, you raise the alarm and start analyzing the system more closely. So let me just finish up real quick with this is just a summary. Here's good old PSXView. So the reason I put this presentation together was partially to get people to stop, as a matter of standard practice, just pulling the plug on the system and imaging the hard drive. As I mentioned, I'm doing work with law enforcement right now. That's still the standard operating procedure for a lot of law enforcement organizations. But if you can, if the system is live at the time you begin interacting with it and you have the tools, I beg you to please do a memory dump of the system. Even if you don't have the ability to analyze the image, somebody later is going to want that memory image, somebody like me. So please, try and do a live capture of the memory on the system. Now, the reason law enforcement agencies are worried about doing this is they say, oh, well, you're modifying the state of the system, you're corrupting the forensic integrity of the system. Well, okay, yes, I have to run a process on the system, and yes, that changes the state of the memory on the system and makes various other changes to the system. But, Ovi Carroll, who, aside from being a SANS instructor, is the head of the DOJ CSIP's crime laboratory, right? So, you think this guy knows what he's talking about. He has a very good analogy, which I like to say here. Imagine the memory of the system as being piles of paper stacked up floor to ceiling in a big room somewhere, right? And there's one door into the room. The room is so tightly packed with these pieces of paper that you have to blow the door off the hinges in order to get access to the room. And yes, blowing the door off the hinges will crap up, 5% of the paper in the room. But are you telling me you're not willing to sacrifice that 5% to get the other 95%, which is critical information that will make your investigation successful? I mean, it's ridiculous. Of course you're going to do that, right? So yes, you will, consume some memory by running a memory dumping tool. But the value you get out of that is worth it, right? Totally worth it. So please, if you get nothing out of this, please, take a memory capture of the system. I'm going to try and catch up and answer questions for people. This presentation is available from the last URL that you see on this slide. So deerrun.com/Hal. You'll find the PDF of the slides from this presentation at that URL. this presentation is sort of a high-speed collision of the SANS Forensics 508 and 610 classes, which I and many other fine SANS instructors teach. We've got a bunch of opportunities for you to take these courses if you have some year-end budget burning a hole in your pocket. Alyssa Torres, who's in the chat right now, is teaching it in Chicago in a few weeks. I'm following up in San Antonio a few weeks later. I've got some Forensic 610 dates, and you can go to the SANS website and sign up for one of those courses. If this wasn't enough for you, there's a whole lot of geeky memory stuff going on in Forensics 508, Forensics 610. Forensics 610 will show you how to actually analyze the malware once you've identified it using the techniques in this class. So there's a whole curriculum of stuff. So let me see if I can get to some questions here before we run out of time. So let's see. Yeah, so we had a question about something I said earlier as far as hibernation files. So I mentioned that a colleague of mine was working with a case where they had an encrypted volume. They didn't have a memory image, but they did have a hibernation file on the system, and the system was hibernated at the time that the encrypted volume was mounted. And they were actually able to use hibernabin to convert the hibernation file into a raw memory dump, and then they used a commercial tool actually called Passware to extract the TrueCrypt key for the volume from the memory image from the hibernation file, and they were able to use that to unpack the TrueCrypt container. So yes, true story, actually works, incredibly useful. So yeah, let's see here. So we had a question about memory images versus the page file, right? So the memory image of a system, whether it's VMware or whether it's a live system, is the sort of active memory of the system. But certain pages may be paged out to disk because typically you don't have enough memory to hold all of the running processes on the system, particularly on personal machines like laptops and things like that. So yeah, I mean, sometimes when you're analyzing a memory dump, you will, like for example, try and dump an executable image or something like that, and you will find that pages of that image have been paged out to page file, and so you don't get complete information out of the memory dump, and that's just one of the downsides of memory analysis. There aren't any good tools that I'm aware of for sort of fully integrating the pagefile.sys with the memory image. And I mean, that's difficult, right? Because memory is constantly changing and pages are being moved in and out of memory. This, creating a sort of perfect snapshot that integrates those two is difficult. And usually you can get enough information out of just the raw memory dump without referring to pagefile.sys. It's enough to get useful information. How do you do a memory dump remotely? Well, my personal preference is fresponse, which is a commercial tool. But if you need to do it on the cheap, you can run Win32 or Win64DD remotely via psexec and have them dump the memory image right over the network to a system where you have a netcat listener set up or something like that. And that is a free way of doing that. So psexec from sysinternals and Win32 or Win64DD and a little bit of netcat, and you're good to go. What memory forensics tool do you recommend for use with Mac memory dumps? That would be Volatility, which now has Mac support. I don't know of other good tools for analyzing Mac memory dumps other than Volatility. If anybody knows one, they should throw it into the chat. Is forcing the system to hibernate a good way to get a memory image if you don't have admin rights? Yeah, I mean, it's certainly one way to do it. Obviously, there is some forensic impact to hibernating the system, but, you know, any port in a storm. Is it possible to inject code on a physical host that is hosting virtual machines and have it affect the hosted virtual machines in some bad way? Huh. I mean, in general, if I have hypervisor access on a system, so if I've got control of the host operating system, there are many better ways for me to impact the virtual machines. And so, you know, once you've got access to the host environment, I can completely harass the virtual machines. You basically have to assume that the virtual machines are completely compromised if I get access to the physical machine. I would probably attack them through some other mechanism than you know, injecting code from the outside. I'd probably just project the module into the virtual machines and then inject it using the normal injection mechanism. Or I'd simply, from the hypervisor, steal whatever information out of the virtual machine I needed to infect, and not impact the virtual machine at all. That way it wouldn't be detectable from within the virtual machine. People are mentioning that the HB Gary tool does try and stitch the memory dump and the page file together. So if you look at, you know, HB Gary's responder tool, it tries to do some pushing together of the page file.sys and the memory dump. So, you know, we get the question we always get about malware using GPUs in order to execute. Yeah, we've seen, you know, certainly we've seen malware that does that, more in the proof of concept stage in my experience than in actual reality. We're getting some Mac memory stuff, Macquisition from Black Bag, Mac memory dumper. So I'd forgotten about the Black Bag tool. So shouts to Drew and the crew at Black Bag. Okay, so I'm actually over time here, so I'm going to wrap it up. You have my email address on the slide here and my Twitter handle. So if you want to ask additional questions, you're more than welcome to contact me by email. As I said, the slides are available from the last URL. And you know, thanks everybody for showing up. I think we had 400 people at the peak. So thanks again, everybody, and we'll see you on the next webcast.
Thank you so much, Hal, for your great presentation and for bringing this content to the SANS community. To our audience, we really appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.